What's good, my statisticians? This is Professor Sampson from PS I Love Math, back with another statistical banger. So we are going to continue our talk with confidence intervals with two samples, but we're going to talk about when the standard deviation is unknown. The standard deviation of the population is unknown because remember, it is rare that we do know the standard deviation of the population. But if you want to check out when the standard deviation of the population is known, look at my video at the end of this video. Let's get started, and don't forget to like, comment, and subscribe. Let's get started. So we do have a little bit of background information to do before we jump into the problems, because there needs to be an explanation a little bit different from when we know the population standard deviation. So let's take a couple notes here. So as I said, we're comparing two population means when sigma is unknown, and these are independent samples, and we talked about independent samples in our last video. We're talking about these independent samples which have nothing to do with each other. When we're comparing two population means and sigma is unknown, the variance comes into play, because we're going to have to know whether the variance is the same or the variances are going to be different. That's going to play a major part in your error, which means it's going to play definitely a major part in your answer. Well, when are the variances are the same? So when we're talking about variances being the same, when would they be the same? What kind of example? Well, if I'm a basketball player and I'm shooting a ball, and the ball are made by different companies, then the variation is going to be the same because I'm the one shooting the ball. So I'm using the same arch, I'm using the same speed, I'm using the same velocity, I'm doing the same thing. So the variance is going to be pretty much the same. However, if there are different people shooting different balls, then the variances are going to be different depending on those people and how they arch their hand and how their velocity is when they shoot the ball. When the variances are assumed to be equal, so when the variance is equal, is assumed, now we don't know, we can call that pooled data because we can pool them together. We call it pooled, P-O-O-L-E-D. Or some books call it combined. Meaning if the variances are assumed to be equal, we can just combine them. We can pull them together to do a good estimate of the population variance because it's the same. When the variance is, like I said, with the two different ball players, is assumed to be unequal, then we call that, of course, unpooled. We can't combine those together. So what's the difference in the two? Well, you'll see when we work out problems, the difference in the two is the error. When you're using pooled data, the error, all right, the error formula is just like the error formula minus that is T alpha over 2. It's just like the error formula that we used when sigma was known. It's the exact same error formula, but it's going to be T alpha over 2 because the standard deviation of the population is unknown. And of course, since the standard deviation of the population is unknown, we're going to use what the sample standard deviation. So if you look at this and compare this to the other formula, it's exactly the same formula, only we're using T alpha over 2 and sample standard deviation as opposed to population standard deviation. This is when we have pooled data, meaning that we assume that the variances are equal. The error is much more different when you assume that the variance is unequal. Still have T alpha over 2, but this is a long formula. And I will show you this formula when we do a problem times a whole nother square root. So this is when the variances are unequal. Two different errors. So I wanted to point that out before we got started with problems so you would see where they were coming from. All right, so now let's get on with these problems. Is it worth pursuing a doctoral degree in education if you already have an undergraduate degree? I have my doctoral soon enough. It won't be in education, in statistics, of course. But anyway, one way to help make the decision is to look at the mean incomes of these two groups. Suppose that 19 people with bachelor's degrees in education were surveyed. Their mean annual salary was $28,500 with a standard deviation of $6,800. 11 people with doctoral degrees in education were found to have a mean salary of $55,500. Why did I make twice as much as that? with a standard deviation of 10,200. Assume that the population variances are not the same. Construct and interpret a 90% confidence interval to estimate the true difference between the mean salaries for people with doctoral degrees and undergraduate degrees in education. Woo! When I saw that salary, I could barely read, girl.
Ain't nobody got time for that.
So we have two samples, and we're going to go back. Remember, we label our samples. And as I spoke to you before, how you label your sample is important in reference to making sure that you interpret it properly. How you label your samples won't matter. Suppose 19 people with bachelor's degrees, right? Their mean annual salary and their standard deviation. And these all need ones next to it so you can distinguish between the first sample and the second sample. And then the 11 people who had their doctorate is N2, X bar 2. Can barely write it, and S2. So that should be all of the information. 90% confidence level. Alpha is 1 minus 0.90, 0.10. We're looking for a confidence interval, so that's alpha over 2, 0.10 over 2. Back to what we've been doing. Alpha over 2 is 0.05. And we're looking for T. Why are we looking for T? Because the standard deviation of the population standard deviation is unknown. The population standard deviation is unknown. We're going to use a T. So we're looking for T of 0.05. And we don't have to do 1 minus because remember T is right tail. T is right tail. So we're looking for T of 0.05, but we need degrees of freedom. And degrees of freedom, of course, is N minus 1. Now, of course, you have what? Two N's. You have N1 and N2. So you're going to subtract those. Now, in your calculator does this big, obviously, it's a mini computer. So it does this big formula to figure out degrees of freedom. And it doesn't give you degrees of freedom as a whole number.
Oh my God!
So when you're doing these by hand, you're going to use the lower of the 2 degrees of freedom. You're going to use the smaller. So for example, degrees of freedom for the first one, 19 minus 1, which is 18. And the degrees of freedom for this one is going to be 10. So we're going to use 10 when we're looking up this on our chart. So let's flip over to our chart and take a look at that. So we're looking for 0.05. That's in 2 tails. Well, that's in 1 tail. And we're looking for what? 10 at 0.05. And this should be pretty easy. This is actually easier to read than the Z chart because up here you have the total in the 2 tails. The area in the 2 tails is 0.10. So our T alpha over 2 looks like 1.812. So here's the formula here. So we'll have 28,500 minus 55,500 minus E, etc. So then we have 28,500 minus 55,500. You get negative 27,000. That the population variances are not the same. So let's take a look at the formula chart, and then we're going to assume, right, that the variances are not equal. So we're looking for the E where the variances are not equal. And right here, you see this formula says unequal variances. So now we just need to plug that one in. And remember, this one is exactly like the last one, only the T alpha was a Z alpha, and the standard deviation of the sample was the standard deviation of the population. The error equals 1.812. So let's pop this in our calculator. 1.812, and we have the square root. And again, I'm going to use the fraction bar, but make sure you know how to put this in. 6,800 squared over 19. So you have your margin of error, 6248, 606, 803. So that's your margin of error. And now we need to go to our calculator and put everything in. That test. And what type of test we're doing? We're doing 2 samples. We're doing a t-test, and we're doing an interval. So all the way down here, right? And we have DATs, not data. And then we're going to input our stat. Is this pooled data or unpooled data? Since we know the standard deviations according to the question, let's go back to the question. It said that assume the population variances are not the same. So they are not the same, so we cannot pool them. No, it's not pooled data. And if you select yes when you should select no, you'll get 2 totally different answers.
Oh, hell no!
Okay, so we have our answer here. We'll interpret it in a minute, but take a look at those degrees of freedom that the calculator figured out, all right, from its intricate formula. So don't take the degrees of freedom off the calculator. The degrees of freedom are going to be the lower of the two samples, not this. Negative 33,039, and then negative 20,961. So negative 33,039 less than mu1 minus mu2 is less than negative 20961. So we have our interval. That was the first part. And now, of course, we have this as construct and interpret the 90% confidence interval. Now, one of the things that I usually do when I'm working these out is that I usually say, read the question and word my final conclusion in reference to the question. So what I mean by that is that I would usually write doctoral students first in my interpretation in reference and compare them to undergraduate. Now, remember what I told you last time. You have to follow this. Your first N1 had to do with students with bachelor's. So your interpretation, if not appropriate, needs to start out with bachelor's, but you have to do it appropriately. Mine is going to start out with doctorate because the question was between the mean salaries for people with doctorals and degrees and undergraduate. So I would have probably, had I been doing this problem myself, I would have probably had N1 be the doctoral students.
I am so confused.
But it doesn't matter. That's a preference, a personal preference thing, not a requirement. So my interpretation, we are 90% confident that the annual mean salary for people with, and look at how I'm wording it. Again, you do not have to do this with doctoral degrees in education, is between, now look at my wording, 20,961 and 33,039 greater than the mean. Okay, you see how I flipped that just to show you interpretations are fine. I put, we are 90% confident that the annual mean salary for people with doctoral degrees in education is between 20,961 and 33,039 greater than the mean annual salary for people with undergraduate degrees in education. You could have worded it that we are 90% confident that the annual mean salary for people with bachelor's degrees in education is between 20,961 and $33,039 less than the mean annual salary for people with doctoral degrees in education. You see how you had to switch the numbers, that 20,000 is, more than 33,000 is more than 20,000. So please don't just write it like this. Do an interpretation means that you have to look at the work and see what the interpretation is going to be, not just copy word for word. Because if you put 33,000 first and 20,000 second, I'm gonna look at you crazy because numbers don't go in that order. And another thing to watch, to look at for this particular one, is that you don't have that additional sentence for the confidence interval containing zero, because this confidence interval doesn't contain zero, which means that there is some kind of difference, that we have determined that there's some kind of difference because zero is not in the confidence interval. So if you wanted to add something, you could say, since the confidence interval does not contain zero, then the data does provide evidence that the two population means are. So you could do that if you wanted to add on a since. But I only usually put in since the confidence interval contains zero is when it contains zero. When it doesn't contain zero, then this statement is good enough. I hope this made some sense. I actually want to do another one.
You're joking. Not another one? Oh, for God's sake, I can't stand this.
Steve believes that his wife's cell phone battery does not last as long as his cell phone battery. On 8 different occasions, he measures the length of time his cell phone battery lasted and calculated that mean was 24.3 hours with the standard deviation of 6.1. He measured the length of time his wife's cell phone battery lasted on 9 different occasions and calculated a mean of 22.8 hours with the standard deviation of 8.3. Construct and interpret a 95% confidence interval for the true difference in battery life between Steve's cell phone and his wife's, assuming the population variances are the same.
90% of the time, I have no idea what the fuck I'm talking about.
So let's get into it. Let's start writing down our knowns. Okay, since we already know this is going to be a T of 0.025, and we know that the degrees of freedom is 8 for this one, and the degrees of freedom is 7 for this one, so we're going to use 7 at 0.025 and 0.025 2.05, 2.365. So here's our new E formula. As you can see here, it's a lot. 2.365 is how we started off. And we need to fill in all of this stuff and just fill in everything. I'll give you a chance to fill in everything.
Whoa, that money clip us now, the new now looks like. Whoa, upgrade her diamonds, now her girlfriends are like. Whoa, 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 whoa.
Okay, let's see about putting this big old hot mess into our calculator. Again, if you don't have the fraction bar, then there are several things you're gonna have to do. Maybe instead of putting in 8 minus 1, you put in 9. Maybe you do the whole bottom first and then do the top. Lot of input, but here is your margin of error, 8.453023. Okay, and now we can go and put everything in our calculator. Stat test. What type of test is this? 2-sample T interval. Stat, and we're going to put in all our statistics. All right, confidence interval is 0.95. And the question is this pooled data this time? The answer is yes, because the two samples are the same. So the sample variances are the same. So we're going to go with yes. And here's the answer. That's your confidence interval. Now we need to, says interpret, of course, construct and interpret a 95% confidence interval for the true battery life. We're going to start off with Steve's cell phone because the question said between Steve's cell phone and his wife. We are 95% confident that the mean battery life for Steve's cell phone battery is between 6.1 hours less and 9.1 hours more than. Remember, you have to take both of those into consideration and the rest, the mean battery life for his wife's cell phone. Now we need to look because this interval what? All right, this interval contains 0. All right, this interval actually contains 0. So now we have to the rest of our writing for our interpretation because it contains 0. So we would go on to say, since this confidence interval contains 0, the data does not provide evidence that the two population means are unequal. So we are 95% confident that if we did this over and over again for their cell phones, that Steve's cell phone battery is between 6.1 hours less than and 9.0 hours more than the battery life for his wife's cell phone. However, since 0 is in there and we don't know, the two means could be equal. So since zero is in our confidence interval, then this data does not provide any evidence that the two population means are unequal. Hopefully that makes sense. So anytime your confidence interval contains 0, you need to make the statement that yes, we did this and we found out that it could be between these two, but he's trying to figure out if these two means have a difference, or that they are going to be not equal. And we don't have any evidence to show that they're not equal because according to our confidence interval, they could be equal because 0 is in our confidence interval. So that means that his phone could be 8.2 and her phone could be 8.2, which means that it will be 0. That means that there will be 0 difference between the two. So if there's 0 difference between the two, then he doesn't have evidence to say what he said at the beginning, that his wife's cell phone battery does not last as long as his. He doesn't have evidence to prove that. He has evidence that it's possible that it does not, even though he believes it does. Whew. Okay, that was a whole lot of mess. This is a good video to go through. There are no other videos on the internet comparing two samples using the same variance and different variances. This is Professor Sampson from PS I Love Math, and I'm out of here. I can't even dance to my song. I'm so tired.
Look somewhere else, he'll find nothing. Just give it up. I'm not your girl, 'cause I only